Hello and welcome to lesson 6.2, Equations of a Plane. So in 3 space, a plane is like a sheet of paper and can be defined in many different ways. So the plane x equals 4 occurs when all x values are equal to 4. However, the values of y and z could be any value. So some points that could possibly exist on this plane are 4, 0, 0, or 4, 1, 0, or 4, negative 2, 0. Could be 4, 3, 5. Could be 4, negative 2, negative 2. Could be 4, negative 6, and positive 3. Doesn't matter what the y and z values are, but as long as the x values are all 4. So let me show you how you actually draw this. So let's first label our axes. Okay, so label our axes. Now, 4, 0, 0 is this point right here. 4, 1, 0 be this point along here. 4, negative 2, 0 be this point along here. You'll notice all the points actually lie on this line right here. Well, all you have to do is now take that line and project it into 3 dimensions. So you can project it upwards, or you can project it downwards. And then you get a plane like this. Looks like you're a sheet of paper. Now, it might be difficult to see on this actual drawing right here, but you can also use a program called Geogebra to actually take a look at this. Sometimes you also have to type in the words 3D in order for it to activate properly. And Geogebra is a free online graphing program that you can use. And you can actually type it in as x equals 4, and you will be able to actually rotate the graph and see how it looks. Okay, so what about the graph of x plus 2y equals 4? Well, let's find some points that satisfy this first of all. Some points that might satisfy this are 4, 0, and 0. Also sometimes called the x-intercept, or the point 0, 2, 0. Excuse me, which is called the y-intercept, or even a combination of things like this, 2, 1, 0. As long as the x and y values add up to be, or are summed in this equation that you can solve right here. It doesn't matter what the value z is. So I could also use 4, 0, and 1. I could also use 0, 2, and negative 1. I can also use 2, 1, and 5. So let's start up by graphing what this looks like. Again, make sure you label your axes. You need to know where those values are. Four, 0, 0 is here. 0, 2, 0 is right here. 2, 1, 0 is right here. So you'll notice that these all follow the same line. And again, you can project this into 3 dimensions. And again, get your shape for your plane. Something to notice here, from our first expression, this is parallel to the y-axis and the z-axis. Or if you wish, another option, parallel to the y-z plane. So you can also describe the y and z as its own sheet of paper. Whereas this expression that we have right here is only parallel to the z-axis. And when it's in this format, right here, x plus 2y equals 4, you can see there is no variable z. And it's parallel to that z-axis. Okay, so notice that we have the scalar form of a plane here, given by the values ax plus by plus cz plus d equals 0, where a, b, and c are integers. Values have to be there in their lowest terms, just like as in standard form, and the leading coefficient must be positive. So similar rules, just now we're adding an extra dimension for 3-dimensional space. But you can see that this scalar form of a item is for a plane, not for a line. Just as like what we covered in our last session. So, what we're going to do is we're going to determine 2 vectors that are parallel to this plane. So in order to find 2 vectors that are parallel to the plane, you first need to find 3 different points that sit on the plane. And those could be any points you wish. So one possible point that I can see is a possible x-intercept. 3, 0, and 0. You can do the same thing for the y and z intercepts if you'd like. Or you can find some other points that would make this still true. So another possible point is 3. We can make this one 2 and this value 1. That would still equal 0. So you can choose anything that would work out that would make this true. You can make this one 2, you can make this 3, and this one 0. So you don't necessarily only have to use the x, y, and z intercepts, but you can use any intercepts that you like. So now that you have this option, 2 vectors that are parallel in the plane, would have to be created by directions between 2 vectors. So from one point to another point. So there's one vector. Another possible vector would be another subtraction. So how about 2, 3, 0, subtract 3, 0, 0. As long as these two directions are not the same, you can define your plane. Okay, so also in 3 space, there are different ways to actually express the plane. As we saw, there was scalar form. So if you did have a plane like this and you wanted to get to any point P from the origin, call it O, you can take any starting reference point on the plane and add any scalar multiple of the vectors A and B, where A and B are non-collinear vectors. So you can also come up with your vector equation of your plane. And your vector equation looks almost like the vector equation of a line, just with an extra directional vector. So it has a starting point. It's called a starting point x0, y0, z0, plus some scalar multiple of the vector A, which we'll call a1, a2, a3, and any scalar multiple of the vector B, which we'll give by b1, b2, and b3. So if there's there's a vector equation, you could probably guess there's also parametric equations. And again, it splits it up by basis of the components. So your x component is x sub 0 plus s times a1 plus t times b1. Your y value is y sub 0 plus s times a subscript 2 plus t b2. And your z component is equal to z sub 0 plus s a3 plus t b3. And follows similar properties. But again, you have to have two non-collinear vectors right here in order for this to work out, and 1 point. So let's find the vector equation of the plane that contains a line from the point 2, negative 3, 4 in the direction 2, 0, negative 7, and also contains the point negative 1, 1, 5. So based on this information, I already know one direction. One of the directions is 2, 0, negative 7. But I need another direction. And again, this direction has to be different. So you have two other points. What if we subtract those? As long as the second direction does not equal the first one, or a scalar multiple of it, we would be fine. Okay, as you can see, this second directional vector does not match the first directional vector. So because we want the vector equation, all we need is a point. So choose any of the starting points. Add a scalar multiple of first directional vector plus a scalar multiple of the second directional vector. In our next lesson, we will see how to actually change vector or parametric equations into scalar equations. And thus concludes this lesson.